Hi, in this class, we want to look at dimensionality reduction, which in this section we call the 2D embedding. And for this class, we will be trying to use the t-SNE and PCA and also MDS as methods to reduce dimension of a particular data set. So basically, the goal is to try to reduce the dimension of a large chunk of data set and using several different approach. One of them is the T-distribution stochastic neighborhood embedding approach. The next approach we'll be comparing it with is the principal component analysis, and also we'll be using the multidimensional scaling approach to as well reduce dimension of our two-dimensional embedding data set. All right, so to do this, I would like to share my screen, and we can take it off from there. So, as always, there's always the need for us to import all relevant libraries that would help us to be able to perform this dimensionality reduction. Basically, we want to reduce the dimension for the purpose of data visualization in order to be able to look at our data set in a more clearer picture. And for the purpose of this experiment, we'll be using the MNIST digits data set, which is a small version, and it includes the features of the scikit-learn. So in order to start, I would like to populate the interactive namespace from NumPy and matplotlib using PyLab, then interactive line. And after that, I would also like to import a seed data set, a random seed data set of around, you can take maybe a random seed data set of around 42. For the purpose of this experiment, we can just take 42, for instance. And another thing I would like to do as well is to import some libraries from scikit-learn. In this case, we want to import this library to be able to load the data sets that we need to use for this experiment. In this data set, we're importing the load digits data set from scikit-learn. So call it load digits data set. Now you can see clearly from here that we have three different types of data set that are stored inside scikit-learn. One of them is the diabetes data set. The next one is the digit data set. And the next one is the line narrowed data set. So for the purpose of this experiment, we just pick the digit data set. And also, because we are going to be using the T-distributed or T-distributed stochastic neighborhood embedding approach, we also want to import it from sklearn. So we call it sklearn manifold, and then import t-SNE, which is a T-distributed stochastic neighborhood embedding. Now, having done that, we would also like to define some significant parameters or features which will be used for plotting the graphs, that's the charts, which is the visualizing the dimensions of the various digits that we will be analyzing. So in this case, we can define a function called plot_mapping, and plot_mapping we want to define it with the figure size, and we use fig size. So we have fig size as usual, and then we define a size. We want it to have 8 by 6 in this case. And after that, we can also define the colors we want it to come with. So we want cm.tab, let's say 10. In this case, we pick 10. And then we can also move on to use the NumPy features, which we had already imported using the PyLab in line, which is the interactive namespace, which is for NumPy. So here we say the line space, which we are pulling up from that. So we say the namespace. So we have 0, 1,9. And after that, because we want it to iterate over a range, so we have for I a range of 9. So for I in range of 9, we pick a selector, which is equals to Y, which is also equals to I in this case. And then we have the axis. And then we have the axis, which is equals to X selector. The axis equals to X selector. And we have X is equals to X selector. And then we have scatter. At this point, we want the plots that we'll be visualizing to be a scatter plot of the axis from the distance to 0. And then we also have, say, the axis from, say, the distance of 1, the dimensions. Then lastly, we also wanted to have a label which is equals to a string of all the values that are iterated from I. And after we've done that, we can also decide to pick a color feature. So we say color equals to colors which we had defined earlier on. And then we want it to iterate over I. And S is equals to 0, 16 in this case, then alpha, which is equals to 0.75. And also we want the edge color to be equals to K. So the edge color to be equals to K. And the edge color is equals to K. And lastly, define the legend. So we want it as well to come with some features of the legend, where we turn off the axis as usual. So we turn off the axis in this case. And in this case, we just want the plot to display without it being interrupted by some form or some characteristics of the axis. So I'm going to try to run this and see. And that is executed successfully. So we've defined the auxiliary function that will be used for the plotting. The next thing we want to do now is to load the data set. So we're going to use a tiny version of the MNIST data set. The images in that data set are 8 by 8 in pixel in dimension. And then there are images of handwritten digits. The data set includes, they're included in scikit-learn library. So we're going to have digits equals to load underscore digits. And then we have X equals to digits dot data, and Y is equals to digits dot target. So we've assigned the values inside digits. This digit data set we've assigned it to digit, and then we'll split it into 2. The target data set inside digit is assigned to X, and the target, the data value inside digit is assigned to X, and the target data set is assigned to Y. So having done that, the next thing we want to do is check the shape of our data set, so we can be able to see what the shape of the data set X and the data set Y. So we can have print X shape, we check for X. In this case, we can be able to see that it has around 1,797 examples, each of 64 dimensions. And we can also do the same thing for Y. We can see Y the shape. In this case, we can also see the number of examples, and also, okay, we see clearly it does not have a dimension, so we don't really bother about the Y value because it's a target value. Whereas the main data set is in the X, in the X variable. Now, having splitted them into this format, we want to show or view the image of a particular set or a particular number of these data, because like we said, we're using the MNIST data set and of handwritten digits. So we want to see the figure, how it looks like, having splitted it into 2, target and the real data set. So we have fixed size. In this case, we have fixed size equals to. So we want it to have a 10 by 5 dimension. And the next thing also, we want to use imshow. So for imshow, have X, then we have, let's say we want to just view 200 images of it. So viewing just 200 images, we have imshow 200, and we reshape the data. And then we just want to have 10 by 20 grid of it. That makes it 200. So 10 by 20. And then in each row, we want 8 by 8 because they have 8 by 8 dimension. And after that, we want it to be transposed. So we transpose the data set from 0 to 1, 3. And then we reshape that as well to say, want it to be around 80 to 160 in shape. Now, we also do not want the grid line to show, so we take out the grid. We're using grid bracket false. Also, X ticks, for instance, we want it to be empty, and also Y ticks to be empty as well. Y ticks to be empty as well. And lastly, we want it to come in a grayscale in order to have a proper viewing. So if we run that right now, it's going to display successfully the handwritten data set of around 200 images of 8 by 8 dimension. All right. So horizontally is 20 and vertically is 10. Now, we have been able to view our data. The next thing we want to do is convert this data into is try to use the scikit-learn implementation of the t-distribution and also the principal component analysis, where we also can compare it with the multi-dimensional scale. So the first thing we want to do is to use the t-SNE, which is the first approach. And for this one, you would want to use the scikit-learn implementation of the t-SNE to map the images to 2 dimensions. It might take a while, but we just have to start the process. So we have TNS is equals to t-SNE. And then here we have random underscore state to be equals to 101. And then we have x underscore t-SNE to be equals to t-SNE dot fit underscore transform, fit transform. Then we're using digits dot data. You can either use digits dot data, or since we have already assigned it to x, we can just simply assign it directly to x. Now, we should note that the TNSC gives a different result depending on the initial random starting parameters. In the above line, we set the random state to an arbitrary number to ensure that the result is always the same. And if we try to come back to it and print out the dimensions, we can see here that, for instance, if we print the shape of the initial x, which we had, you see it gives you a different value or a different value with a different dimension, because the goal was to reduce the dimension with the TNS approach. So we have TNS the shape. So if we try to check that, you see that dimension has reduced significantly. All right, the dimension has reduced significantly. For the first one, we see the same examples, but with 64 dimensions. And the second one, the same examples with just 2 dimensions. Having achieved that, we want to plot it against the digits data set and see how it looks like. Recall that we had defined previously plotting a plot auxiliary function, which helps us to plot a chart. So we can say x underscore tsn, comma, then we say digits dot data. Now, if we try to plot this, it kind of like give us, so we have plot, so here we have, instead of data, we can just simply put target. So we are plotting the X underscore T distributed stochastic neighborhood embedding with the target data set. And we can see clearly from this that the t-SNE embedding nicely separates the different digits into clusters. For the most part, you can see how they are separated into different clusters for each of the parts 0, 1, 2, 3, up to 8. They are all well separated without any mixture or confusion. Now you can see how clearly separated they are because we have already split them into much smaller dimensions and we have reduced this significantly. This is impressive because it has never been given access to the target label. So it just simply studied the X underscore t-SNE was not given access to the target data, so hence did not even know how to be able to embed itself around it. So this shows an impressive result. Now, in order for us to learn better about it, it is good for us to compare the t-SNE with the principal component analysis, which is also another type of dimensionality reduction strategy. So now we want to compare it using the PCA. So we have the PCA approach where we see how the components can be better reduced, and if it will be reduced, we want to see how that can impact on the clusterness or the closeness of the digits. So from here, what we want to do is import the libraries for PCA. So we have scikit-learn.decompose, scikit-learn.decomposition, scikit-learn.decomposition, import PCA. One interesting thing about the scikit-learn feature is that we are able to import some of these approaches or these algorithms, this method from it without having to like recreate them over again for use. So which is one beautiful thing about the use of Python in this kind of analysis. So we have them, we've imported PCA. The next thing we want to do now is define the parameters around which PCA is used. So first we have PCA, principal component analysis. We want it to have a dimension 2. And then we have X PCA equals to PCA dot fit transform. So we have fit transform on the data sets on the X data set which we had defined previously. And then for the purpose of visualizing this data set, we also bring in our mapping. So here we have X underscore PCA. Then we have digits dot target like we did earlier on. So we have digits dot target. So if we run this, we'll compare the output between the both of them. You can see clearly that they look different from the previous one. So the previous one had a better fine-tuned cluster, which is clearly seen by how they all relate to the target data. But over here, in this case, the separation is less clearer. Of course, it moves between 0 and 8, but then the separation is much clearer between the digit classes. So this shows that the t-SNE kind of like outperformed the PCA dimensionality reduction approach. Now, we want to also move on and compare all of those two with the multi-dimensional scaling approach. For the multi-dimensional scaling approach, just like the t-SNE and the PCA approach, we can also import, so we have the MNIST, which is a multi-dimensionality dimensional scaling approach. Here, just like in the previous example, we can also import its procedure from the scikit-learn. So we have import MDS, which is multi-dimensional scaling approach. Having done that, we can say MDS is equals to MDS at 2 dimension, and then we have X underscore D MDS equals to MDS dot fit transform. So we have MDX dot fit transform into digits dot data, and we have plotting function the auxiliary porting function which we had previously defined. And then we say x underscore MBS. Then we have x, then we have digits dot target like we did earlier on. Now, this might take a while to finish execution, but we'll just give it some time while we expect the results. So basically, both approach seeks to reduce the dimension of each data set. And we can see that the t-SNE kind of like reduce the dimension proper and kind of cluster the various data points in a much separated way than we saw the PCA did. There is a much closeness between the data points or the different clusters or target data sets in the PCA approach as compared to the t-SNE. So we're going to look at the MDS and then we see which method kind of like outperform the other. These have significant application in dimensional reduction approach. But for instance, if you have a data set and sometimes these data sets have maybe large anomalies and your goal is to reduce these anomalies, it is important that you're able to perform dimensionality reduction to reduce the sizes of differentiation or difference between the various data sets. You will put them in the various categories that you want to use them. So basically, the MDS approach tends to be a bit much heavy and have much slower performance in terms of predictive or clustering or reducing the dimensions of the various data sets that we have selected, which is why you can clearly see that it's taking time to give us the output. But clearly, I would say between the first two, which is between the t-SNE and also the PCA approach, I would always go for the t-SNE because it's based on the T distribution, which is the probability distribution density function, and then it gives us a more robust and effective way of reducing dimensions for our data set. Now we can clearly see from here that although the MDS approach, which is a multi-dimensional scaling process, takes much time, it still produces a bit much similar output or result as the PCA. None of them is close to the t-SNE approach, which also gives us a reason of concern. Now, in the next few minutes, I'm going to introduce one or two more other approaches and see how they are able to provide anything closer to the t-SNE approach. The next approach I want to introduce, which is not part of what I was aiming at demonstrating today, is the isomap. The isomap is a nonlinear dimensionality reduction technique. It is nonlinear. It was originally described in the year 2000, and it was considered as a big breakthrough at that time because it kind of like outperformed the principal component analysis and the multidimensional scaling approach. So we're going to look at the isomap, and then if we have more time, we'll look at other approaches and see if they're able to perform as good as the t-SNE. So here we have import, we have manifold, then we say isomap. All right. So having described the isomap, we have iso equals to isomap. If you look closely, the approach is all the same. Define the variable, define the data set, we fit into the data set model. So we have iso.fit transform, iso.fit transform, and then we assign it to our data set, digits.data, which is the training data set, and then we plot. That's all very much easy, right? So we have plot mapping, and then we say x underscore iso digits target. So we are plotting the transformed data set against the target data set. So let's see what happens with this one. I hope it's a bit faster than the previous one. So let's see how good. So you can see that although it did not outperform the t-SNE in terms of reducing dimension, but it kind of like performs better, which is like we said, which was the reason why it was considered one of the major breakthrough in terms of dimensionality reduction. It's a linear approach. I mean, it's a non-linear dimensionality technique, and it has a great application considering its performance in reducing dimensions of data. Other types of approach have also been considered, and one such approach is the autoencoder approach, which is also another example of a nonlinear dimensionality reduction. Now, basically, this one, the autoencoder approach, mostly is used as a deep learning approach, and we could also adopt to look at it. So let's try to add that to our list of things we're learning today. So we've looked at that, and then here we're looking at the isomap. So let me just name this here. So we have the isomap, and lastly, we can now take another approach, which is the autoencoders. Autoencoders. All right. Autoencoders, which is the last approach we'll be considering in our dimensionality reduction today. All right, so for the autoencoders, we'll be making use of Keras in this case. So we'll be using layers from Keras and models from Keras to be able to perform standardization and scaling process of the autoencoders to reduce the dimension. So in this case, I'm going to have from Keras.layers, from Keras.layers, import have input and dense. All right, from Keras.models, import model. Okay. Also, we'll import the rectilinear learning unit, which is the ReLU. So we have Keras.layer import ReLU, which we call the rectilinear. So, or we can also simply say from TensorFlow. So we can either import it from TensorFlow, or we can also import it from Keras. So Keras.layers import ReLU. All right, good. So having imported the library, the next thing we want to try, so we have TensorFlow. So we have Tensor. Right. Having imported the library, the next thing we want to do is scale our data set. So first, we need to scale the data set to have zero mean and unit variance. So we want to scale the data set that we are going to be using, which is our existing digit data set. So we'll have from scikit-learn.preprocessing, scikit-learn.preprocessing, import standard scaler. So we're going to be using that to try to scale our data set to take our mean to 0 and the variance to 1. So we have x scaled equals to standard scaler dot fit transform x. And don't forget that x in this case is equals to digits dot data. So we have that. And the next thing now we want to do is to define our autoencoder. So we want to define the architecture of the autoencoder neural network. And in this autoencoder that we want to define, we want to use 3 encoder layers and 3 decoder layers with 1 embedding dimension of 2. So let's define our autoencoder neural network. So first we start by saying encoding dimension, which we say must be equals to 2. And then we have to define the deep neural network. So let's have input underscore image is equals to input, which we can imported earlier on. So we have shape equals to x dot shape, and then we have encoder, or encoded equals to that. Then we have that 2. So say the activation here is equals to 10, and we want it to contain input. So we have input underscore image we have defined earlier on. All right. Then the next thing is, so because of time, I'm going to take out all of this and just keep pasting. So we have, let's take out this so we can save time. So we have encoder. So now we keep reducing the dimensions from 32 to 16, from 16 to 8. So we have, this is encoded. And encoded. Then the next one is dense 8. Also have the encoded with the last encoded. So we have the encoded. Then after that we have this is encoding dimension, Then we have that, so we come equals to the encoded. All right. The next one is for decoding. So we say we have 2 dimensions. We have 3 encoder layers and then 3 encoder decoder layers. So the next one is decoding. So we have decoded. So we have decoded. Then so we start from 8 to 16 to 32. You know, since we encode from 32 to 16, from 16 to 8, so we have to decode from 8 to 13, and 16 from 16 to 32. So we have decoding 8, and then we have input encoded, and then the next thing we have is the next one, which is 16, and then instead of encoded here, we call it decoded. Okay, decoded, and then the last one we have is 32. So we are decoding backwards. All right. And lastly, we can also now import the last part, which is, instead of that, we have x dot shape at position 1. Then here we have it as decoded. All right, let's see if this is going to, of course, we have an error here because we have something missing in this case. So let me put that by mistake. We expect the error to run. So I'm going to stop it. So it's still running. All right, so yes, that's what's going to happen. So let's try to restart it again. At this point, it ran successfully. Now, having done that, the next thing we want to do now is model our encoder and decoder together and form the auto encoder, which we'll eventually use to be able to reduce the dimension of the data set. So we have encoder to be equals to model, which we have imported earlier from Keras, and then we have input equals to input image, input underscore img, and then we have output equals to encoders, output equals to encoded, and auto encoder dot compile. Let's compile. So here we optimize, we use the optimizer adder. We use the adder optimizer, and then we use okay, so this is, so for this one, first of all, define the auto encoders. We have equals to model as well. Then we say input equals to the input inputs underscore img, and our output equals to decoding. So we have 2 of that. So let's see what happens if we try to run that. That's good. Next thing I want to do now is define our encoder.compile. Encoder.compile and then optimizer. So we have optimizer equals to Adam, and the loss function, that's the error metric, which is the loss function, equals to the mean square error. Also, we have the autoencoder and encoder.compile. Also encoder.compile. So we have optimizer, the same thing, item, and we say the loss function in this case is mean square error. Now, having done that, we can also now we now want to train our model around some certain number of iterations. So in order to train our model, so we have autoencoder.fit the model. So we want to train this new model. So we have this at scale, and then we have X scaled. Again. X scaled. Now we want to train it with just say 10 iterations, all right? Just because of time. And we want the batch size for the training to be say around 160. I just put that 256. Let's say 256. Then we want it to shuffle through the iteration periods. So we have it shuffle and then the verbose equals to 2. So it means we don't want it. We could either remove the verbose because to 0 or leave it as 2 because we want to see the training function. We want to see how it displays, how it trains the model. We want to see how much losses it will have with each epoch or each iteration in this case. So yeah, brilliant. Didn't really take much time. You can see it has finished, and you can see at every given point the loss function continues to decrease, and the time it takes for the epoch to complete is actually very minimal. So it moved from 0.962 to 0.8050. All right. Now we need to embed the data and then plot the results. For us to, in order to embed the data that we have already trained, we have X auto equals to encoder.predict. So we have X scaled. All right. We have N scale. And then lastly, we can now predict it, or we can now see or visualize our data set. So we have plot underscore mapping. Then we have X also, comma, then our target data set. Y is our target data set and X for data set. So clearly we can see how it has it's performing right here. It clearly shows a different kind of like dimension. So it kind of like spread it a bit much different as compared to the previous ones we had looked at. So you can see all these various approach have shown different types of performance in using the dimension of this data set which we had chosen. And first we have seen the t-SNE, which kind of like cluster the data set into different structures. And then we have seen how the PCA they perform. We've also seen how the MBS perform. And we have also seen the isoborn, how we try to outperform the MBS and PCA and come close to the t-distributed stochastic neighborhood embedding. And lastly, now we see how the autoencoders try to produce a better results with training model. So this is how we can reduce dimensions of our data set in order to reduce anomaly or to try to prepare or preprocess our data set for future engineering. Thank you.